Welcome to video one of topics 111 and 112. Continuity is actually a big deal in calculus. And so please don't be misled by the fact that this note sheet is only one page front only. This is going to give us kind of the big idea, the definition, and the big ideas, but we're going to be practicing a lot this week um, in our next session and in the follow-up session. We're doing continuity week because it's a big part of making sure that we can take derivatives. So we're gonna dive into it. We'll probably do this in two videos. I think we can get both of these or all of this done in two videos. But let's see. So what we talked about in the previous topic 110 about identifying different types of discontinuities and then how to fix them led us to the definition of continuity, which is in this big box. So we know that a function f is continuous at some x value. I don't know what x value, so we'll call it c. It could be any x value. We can check if a function is continuous at an x value c if three things happen. Number one, is f of c defined? In other words, the point, the y value exists. That's what that means. F of c is defined means there's an output, right? Second condition, if the limit of the function as x approaches c from the left is equal to the limit of the function as x approaches c from the right. That's another way of saying there's a limit. The limit exists. And then the third condition is, does the limit of f of x as x approaches c equal the value of f of c? Does the limit equal the y value at the point? So I got to check. Does the point exist? Does the limit exist? And then are they equal? We have to check both sides. As when we're checking condition two, especially when using a piecewise function, we have to find both sides to verify that the limit actually exists. So when we look at these different scenarios, can we think of a graph where condition one is true but condition one does not hold? Can we think of a situation where the function value does exist, but the limit does not exist? Is that possible? If you'll pause the video for a little bit, I guess you can think about what that situation might look like. Here's a possible situation. Remember, according to this, condition two doesn't hold. That means the second condition isn't met. That means the limit doesn't exist. So it could be that my function is going, yep, and there's a point there, but then it skips and then it does this, right? If I have two pieces where there's a jump discontinuity, this is an example of the limit doesn't exist because the left and the right are not in agreement, and yet there is a y value here at c. It's wherever this point is because that's where it's defined. So the y value exists, but the limit doesn't. Okay. Can you think of a situation? Can you draw a graph where condition two is true, the limit does exist, but condition one does not hold? There is not a point defined or in existence at that x value. I'll let you pause and think about what that might look like. Our graph could look like this. By the way, we don't know where this x value of c is, so I'm just putting it here and labeling it that way. Does the limit exist? Sure. From both sides, it's approaching whatever this y value is over here. But does the point exist? Well, no. There's no hole there. I mean, there's a hole there. There's no point there. So condition one doesn't get met. Condition two does. So in both of these cases, if you'll notice, we have discontinuity, right? So can we make one and two true, but three not hold? So what we're really doing is we're looking at, there's only like limited number of ways that a function is not continuous, right? And so here are the different ways that we can have discontinuity. Either there is a y value but no limit, or there is a limit but no y value, or there is a limit and a y value but they're not equal. And something like that would resemble this graph. And I'm going to use a similar graph to the second one, where I'm going to go boink, 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 and this is still at C, except I am going to define a point up here. So there is a y value, that's where the point is. There is a limit, that's where my left and right pieces are approaching, but they're not the same. In each of these cases, there is a discontinuity. If I have all three conditions met, then I know that the function is continuous at that particular x value, which we're going to check here with example 2. Can we show that the following function is continuous at x equals 1? Well, let's go in order here. Condition 1. Does the function value exist? Is there a y value? Well, which piece, the top piece or the bottom piece? Is there one that has an equal sign? Because that tells me when x equals 1, then that's the piece I'm going to use. And I notice, I'll use a different color, I notice that it's right here. So that means the bottom equation is responsible for us finding the y value. Minus e to the 1 minus 1. Ooh, okay, so now we're getting, without a calculator, right? So this is, let's see, minus e to the 1 minus 1. 1 minus 1 is 0, so this is minus e to the 0. The natural log of 1, and actually any logarithm of 1 is always equal to 0. So then 0 minus any number to the 0 power is equal to 1. That equals negative 1. There is a y value. It's negative 1. When x equals 1, the y value, the function value equals negative 1. Condition 1 is met. Condition 2. Does the limit exist? Well, this is a piecewise function, so we have to check the limit as x approaches 1 from the left side. And we have to check the limit as x approaches 1 from the right side and see if they match. I'm sorry. Yeah, and see if they match. Well, the right-sided limit, I'm using the same formula that I did for part 1. So this is just going to be negative 1. Because I'm going to do direct substitution anyway, right? The left-sided limit, I have to substitute 1 into my formula, and 2 times 1 squared is 2, minus 1 is negative 1. So therefore, the limit from both sides as x approaches 1 of this function does exist, and it equals 1. So from the left side, it's going towards one spot. From the right side, it's going towards the same spot. So therefore, boop, there it is. So now the last piece we need to check, are they the same? Well, yeah, f of positive 1, we said over here on the left side equals negative 1, and that is the answer to the limit. So therefore, f of x is continuous at x equals 1. So f of x is continuous at x equals 1 because the function value exists, the limit exists, that's what we checked, and they are the same value. And they are, why don't we just say, and they are equal. And that's how we check for continuity. It's a 3-step process. Y value, check. Limit, check. Are they equal?